Hello, linear algebra students. Let's go over this previous test in preparation for our third midterm. We begin with the first question, which is least squares. We are given A, given B, and we want to find the least squares solution to the system AX equals B. Well, we start off and calculate A transpose A. We also calculate A transpose B. For A transpose A, well, A transpose, the first column becomes the first row, and the second column becomes the second row, and then we just recopy matrix A. This will be a 2 by 2 matrix. Also, we see the columns of A are linearly independent, and so A transpose A will be invertible. Well, we get 3, we get 0, 0, and 6, which is 1 plus 4 plus 1. Now, A transpose B, I can just recopy A transpose. When we multiply A transpose times B, I get 3 plus 2 plus 1, which is 6. And then I have 3 minus 4 plus 1, which is 0. And so maybe I'll write in black my normal equation. My normal equation, well, this is always consistent, and the solutions to this normal equation are our least squares solutions. Now, in this case, we will just have a unique solution because, as I mentioned, the columns of A are linearly independent. We also see A transpose A, without a doubt, is invertible. Okay, so let's calculate A transpose A inverse. Well, this is a diagonal matrix. And so A transpose A inverse, this is one of the beautiful things about diagonal matrices. We just take 1 over 3 and 1 over 6. Now, here's my solution, X star, my least squares solution. What I want is A transpose A inverse, and then times this A transpose B. If we think, say, linear combination of columns, this is just 6 times the first column, which gives me 2, 0. So this is it. This is my least squares solution. Now let's move on to the second part of this question. The second part of this, we want the distance from the vector B, or it says the point 321 to the plane, which is the image of A. Well, we know the shortest link that you can be from B to the image of A is AX star. We know AX star is the projection. This is how least squares came about. And so this distance that they're talking about in number 2, we just want this length B minus AX star. This is another way to say it. This is the least squares error. So first, let's calculate B minus AX star as a vector, then we can take its length. Well, vector B is 3, 2, 1. Matrix A, we can still see, is 1, 1, 1, 1 minus 2, 1. X star is the vector 2, 0. Well, let's multiply AX star. It's just 2 times the first column of A, which is 2, 2, 2. We get 1, 0, minus 1. 1, 0, minus 1. Okay. Well, all I need now is the length of this vector. This is, maybe I'll write this here. We have B minus AX star calculated, and its length is just the square root of 1 plus 1, which is the square root of 2. So this is my answer here in part 2. Well, now we move on. The next question is a determinants question. A and B are 3 by 3 matrices. Determinant of A is 2. Determinant of B is 3. We want the determinant of this big product of things. Well, we have to use properties here. So first of all, this 3 by 3 part of this is really important because you see I have this constant minus 2. So I'm going to have a minus 2 to the 3 here because you factor a minus 2 out of each row. The determinant is linear in each row separately. Then I have the determinant of A times the determinant of A, because a product of determinants is a determinant of products provided they're all square matrices. And then I have the determinant of B transpose is the determinant of B. And then the determinant of A inverse is 1 over the determinant of A. Well, minus 2 cubed is -8. And then I have determinant A, determinant B. And this will be my answer here. So I have -8 times 2 times 3. -8 times 2 times 3, which is -48. So this is my answer to number 2. We have another determinants question. We're given this matrix A, which is 4 by 4, and we want to find the determinant of A. Then we have some other parts. Well, the thing is, if I look at this, I don't see any zeros to start cofactors. I do see, for instance, 1, 2, 3 is here, 2, 4, 6 is here, which is 2 times 1, 2, 3. So that potentially will be a row operation I could take. But even then, if I had 0, 0, 0, and I expanded about this 10, I would still have this 3 by 3 with a bunch of non-zero entries. There's lots of ways we could do this. Maybe I will clear zeros out all underneath this as a first step to create as many zeros as possible before I jump into cofactors. So in one step, we will take, let's see, -2 row 1, add it to row 2. We will take -2 row 1, add it to row 3, and then minus row 1, add it to row 4. So then this will give me a very short determinant calculation. So the determinant of A will equal, first of all, these 3 do not change the determinant. Adding a multiple of one row to another does not change the determinant. And so I have 1, 2, 3, 4. And then we take -2 row 1, add it to row 2. I have 0, 1, 2, 1. Then -2 row 1, added to row 3. This is where I get the 0, 0, 0, and then 2, 0, 0, 0, 2. And then finally, minus row 1, added to row 4, I get 0, 3, 7, 5. Okay. Well, we could continue with row operations if we wanted to, but at this point, I'm in really great shape for cofactors. So first I will expand here, and then the determinant is 1 times this smaller 3 by 3, which I can just copy. We can see, we cross off the first row, cross off the first column, and we get this. And now you see, I can expand here. Here I need to pay attention a little bit to the sign. This is plus, minus, plus, minus. So I have a -2. Or if you want to think about the -1 to the row plus column, this is -1 to the row 2, column 3. This is how we see this is a negative number. And we will cross off the second row, third column. We have 1, 2, 3, 7. 1, 2, 3, 7. And now we have -2, we have 7, -6. The answer is -2. That could have been significantly longer of a calculation if I hadn't started off with these row operations. Now we move on. The second part, for the above matrix, choose all of the correct statements. A is invertible. Yes, it is, because the determinant is not equal to 0. A is not invertible. Well, that's not the case. 0 is an eigenvalue. It will not be, because 0 is an eigenvalue if and only if the matrix is not invertible. A is an orthogonal matrix. This is a no. Well, the determinant is -2. It's definitely not an orthogonal matrix. We can also look at the columns of A and see that they are not unit. They're also not perpendicular, for example. The determinant of -A is negative determinant of A. Not for a 4 by 4 matrix. So E is also false. The last one, F, this is true. This is true for every matrix. In fact, every square matrix that's invertible, say, this would hold. So F is true. The answer here is just A and F. Number 4, We're given a 3x3 matrix. We want to find all eigenvalues, and then we have a second part to this. Okay, we need the characteristic polynomial, fa of lambda, which is a determinant of a minus lambda I. So what we do, a minus lambda I, we just subtract lambdas from the diagonals. We have -1 minus lambda, and then we have 3, 0. We have 4, 3 minus lambda, 0, and then 5, 7, negative lambda. Well, once again, we can use zeros to expand. Cleverly here, I'm going to spin about the third column. So you see, I get minus lambda, because plus minus plus minus plus, or -1 to the 3 plus 3 is the even power of -1. And then you cross off the third column and the third row. And what we're left with, we see it, it's right here, this 2 by 2. So this is what I still have to calculate the determinant of. We have minus lambda, and then we have -1 minus lambda, 3 minus lambda, and -12. Now what we need to do at this point, because I'm trying to find the roots of this polynomial, the negative lambda part, I'm just going to leave out in front. In fact, we can see this matrix is definitely not invertible, so 0 will be an eigenvalue. We knew that before we started calculating. So what I need to do is just multiply all of this out and refactor. Let's do this here. So I have minus lambda. Now under here, let's see what this is. We have lambda squared. We have -3 lambda. We have plus lambda, and then we have -3. Okay, that helped me a little bit here. So now on the inside, I have a lambda squared. I have a -2 lambda, and then I have -15. This factors into lambda -5 and +3. Lambda -5 and lambda +3. Now I can answer the question, what are the eigenvalues of A? Find all of them. Okay, we solve. We have 0, we have 5, we have -3. So we know some wonderful things. For example, this matrix will be diagonalizable because we have 3 distinct eigenvalues. Well, it's not asked, but that's a nice comment. So what are the eigenvalues of A transpose? Well, they're the same as the eigenvalues of A. We discussed this in class and justified it. A and A transpose have the same characteristic polynomial. So we can just copy and paste. Same eigenvalues. The next question, we're given a symmetric 3x3 matrix, and through the various parts, we will orthogonally diagonalize this matrix. The first part, it says, is U, which is 1, 1, 1, an eigenvector for A? If so, what is the corresponding eigenvalue? Well, we can just take and multiply. So when we multiply this matrix times this vector, well, you see, we get 5, 5, and 5. And this is 5 times the vector 1, 1, 1. And so the answer is yes, because, let's see, it's U here. AU is a multiple of U. The answer is yes, and the lambda is 5. The second part, we're asked, is V, which is 1 minus 2, 1, an eigenvector of A. What is the corresponding eigenvalue? Well, we can go about it in a very similar way. Let's just multiply A times V and see if we get a multiple of V. Here, you see we have 1 minus 2 plus 3, which is positive 2. We have 1 minus 6 plus 1, which is negative 4. And then we have 3 minus 2 plus 1, which is positive 2. And we can see this is 2 times the vector 1 minus 2, 1. So once again, the answer is yes. We have an eigenvector, and the eigenvalue is 2. AV is a multiple of V. Well, and V is non-zero, so V is an eigenvector. Now the last one, find a basis for the eigenspace. corresponding to lambda is minus 2. We compute a minus 2i. And then we need to find a basis for the kernel. This is what the eigenspace is here. A minus 2i is just a plus 2i. So let's add 2's along the diagonal. We have 3, 1, 3. We have 1, 5, 1. And then we have another 3, 1, 3. Well, what is going to be the reduced row echelon form? You see, the third row and the first row are the same. So I can just get rid of the third row, and I can also interchange 2 rows. So I have 1, 5, 1. I have 3, 1, 3, 0, 0, 0. But what else is going to happen here? We can kind of see it because you can take 3 times the first row and subtract, and that's going to give you zeros here. Then you could make, this would not be a 1 after that row operation, but you can make it a 1. Then you can clear out above. So when we go to reduced row echelon form, you can see what we will get. We will get 1, 0, 1, 0, 1, 0, and then 0, 0, 0. This is the reduced row echelon form. Okay, so the eigenspace is just the kernel of a plus 2i. We have its reduced row echelon form, and then we know how to find bases for kernels. You see, I really only have one free variable here, t. And then let's see, if x3 is t, then x1 is negative t, and x2 is 0. Now I don't need the general solution, I just need a basis. So we can find a basis here. We can say let t equal 1. This will work. Then we have minus 1, 0, 1. Okay. This would be my answer in this part. Now we have the very last part. We want to use all of the above to orthogonally diagonalize this matrix. Well, we have all of the eigenvectors. The other thing we know from theory is that when you have a symmetric matrix, eigenvectors corresponding to different eigenvalues are orthogonal. And you can check that if you want. So the only thing I need to do to get the matrix S, which should be orthogonal, is I need to normalize the 3 vectors. So let me call them something. Oh, we have U, we have V. Maybe I'll call this one X. Let X equal this vector, minus 1, 0, 1. Okay, now the length of X is the square root of 2. The length of U is the square root of 1 plus 1 plus 1, which is the square root of 3. And then the length of V, we see V, would be the square root of 4 plus 1 plus 1, which is the square root of 6. So now let's write down our matrix S. Let's write down our diagonal matrix D. Maybe I'll do D first. D has eigenvalues along the diagonals. And one eigenvalue is negative 2. Maybe I'll put this here. Then we found 2. And then we found 5. Okay, so this is my diagonal matrix. It's my matrix that has eigenvalues along the diagonal. Then we have matrix S. Now the only thing I need to do is take these vectors, put them in the right order that corresponds to the columns of D, but then I need to make sure they're normalized. So I'll do the x1 first. This is minus 1 over the square root of 2, 0, 1 over the square root of 2. Then, corresponding to lambda equals 2, we see it. It's this vector, which is vector v, has length square root of 6. So I have 1 over the square root of 6. We have minus 2 over the square root of 6, and 1 over the square root of 6. And then finally, vector x was 1, 1, 1, corresponding to lambda equals 5. So we have 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. Now, you can check the columns are unit, the columns are pairwise orthogonal. S is an orthogonal matrix. Let me underline these. S. The first part of 6, we're given the span of a line in our 3 and the 3 by 3 matrix of projection. We don't need to write down the matrix, we just need to diagonalize it. So what do we know? Well, we really have to think about this geometric action. Anything along the line is fixed by projection. So immediately, let's see, we'll start writing our S of eigenvectors, and maybe I'll call it B here, or D of eigenvalues. So this vector, 1, 0, 5, is an eigenvector with eigenvalue 1. But the other thing to think about, I can write a basis for L perp. We can do this one by inspection. If we couldn't, we could put this as a row of a matrix and find its kernel. That would work as well. But by inspection, we see that L perp has basis, while one of them is just E2. And the other one, let's see, we could take 5, 0, minus 1. 0, minus 1, like this. So these are eigenvectors. These map to 0. Every element in L perp, the orthogonal complement of L, maps to 0 under the projection. So what that says is that both of these basis elements have 0 as an eigenvalue. So here is our diagonalization. Here's matrix S, and here's matrix B. We have diagonalized this matrix A. The next question, we're given two 2 by 2 matrices, A and B. Just note that these are diagonalizable. Well, you might just verify for yourself, why is this the case? They're both upper triangular, and for an upper triangular matrix, the eigenvalues are along the diagonal, and we have 2 distinct eigenvalues. Necessarily, we will have a diagonalizable matrix. In fact, B is already diagonal. Okay, the question though, is the product AB diagonalizable? Why or why not? This is a great question. Well, let's calculate AB. If we take matrix A times the first column of B, here and here, this is just 2 times the first column of A. And so we get 2, 0. Okay, now matrix A times the second column of B, this is just 1 times the second column of A, which is 3, 2. So this matrix has 1 distinct eigenvalue. We see it, it's along the diagonal. Okay, it's repeated, lambda equals 2, 2, algebraic multiplicity 2. We can even write that if we want. However, if you take AB minus 2i, this matrix, this is here. We have 0, 0, 3, 0. And this matrix, this has nullity 1. Its rank 1 is also nullity 1, which means the geometric multiplicity of this eigenvalue is just 1. And so that says that AB is not diagonalizable, because we need to have 2 linearly independent eigenvectors corresponding to this eigenvalue, and we do not. So this is why the product AB is not diagonalizable. Now, question 7, V is an eigenvector of A corresponding to eigenvalue lambda equals 1. Is V an eigenvector of A cubed minus 2A minus I? Yes, it is. Well, I'll just start off by saying yes. We have practiced things like this. They are great questions, but we know A cubed minus 2A minus the identity times V. What happens here? A cubed V minus 2A V minus the identity V. Now A cubed V is just 1 cubed V. Lambda is 1 here. And then we have minus 2AV. Well, AV is 1V, so we have minus 2V. IV is 1V. And so what do we have? We have 1 minus 2 minus 1. This is negative 2V. So this is the yes, because A cubed minus 2A minus the identity times V is a multiple of V. And we see the eigenvalue. The lambda is -2. Last question is the true false. We have 5 of them, and there's room to write here. First question says if A is an n by n orthogonal matrix, then the determinant of A is 1. Well, we discussed in class, and you can show that the determinant of A is either 1 or -1, but it doesn't have to be 1. So this is false. But if you want a specific example, well, we can just take something like this, say 1, 0, 0, -1. Really, any 2 by 2 reflection matrix will work here. But this is orthogonal because the columns are unit and perpendicular, and this has determinant -1. So this first one was false. If A is diagonalizable, then A is invertible. This is also false. These are just unrelated. They're totally different concepts. Diagonalizability, invertibility, they are different concepts. And so this one, we can come up with an example. Well, we could use the all zero matrix, for instance. That's diagonalizable. It is, and it's not invertible. But if you want a matrix with at least one non-zero entry, you could just take this. It's diagonalizable because it's diagonal. It's not invertible. Maybe I'll write that. This is diagonal. Certainly it's diagonalizable and not invertible. So this is one example here. Number 3, it says if the determinant of A is 0, then 0 is an eigenvalue of A. This is true. I'm not sure how much there is to write, but maybe I can write something. We know the determinant of, say, A minus 0i. Well, this is the determinant of A. And so if this determinant is 0, it precisely says that 0 will be an eigenvalue of the matrix. Very nice. Next one, if lambda is an eigenvalue for an invertible matrix A, then 1 over lambda is an eigenvalue for A inverse. This is true, and this is in the homework. But let's go over this calculation. So let's suppose AV equals lambda V. What we can do to get that 1 over lambda is an eigenvalue for A inverse, let's just multiply both sides of this equation by A inverse. So we have A inverse A V equals A inverse lambda V. Now, the left-hand side is just V. It's the identity times V, which is V. And the right-hand side, you see lambda is a constant, so I can factor it out in front. We get lambda A inverse V. Now you see A is invertible, so lambda is not 0. And so we can divide by lambda. We get that A inverse V is 1 over lambda times vector V. And this says precisely that 1 over lambda is an eigenvalue for A inverse. In fact, it says that this V is also the eigenvector. Number 5, it says if A equals PB, P inverse, then A and B have the same eigenvalues. This is true. In fact, A and B have the same characteristic polynomial that we discussed in class. Maybe I will just mention number 5 for my reason. This says that A and B are similar matrices, and similar matrices have the same eigenvalues. So this is enough of a discussion. They have the same characteristic polynomials, the same eigenvalues with the same algebraic multiplicity. Well, I think I will just stop here, but this is the end of our previous test. I hope this is helpful, and good luck on our 3rd test. Thank you.